In this video, I'm going to try to give you a problem that puts together all the concepts you've covered in this unit. So let's go back to our poor, overworked spaceship captain. He's gone back to Earth for a well-needed vacation, but now they need him to launch something all the way out of the solar system. So let's assume that the Earth has a mass of 2.9 times 10 to the 24th kilograms. That's actually exactly what the Earth's real mass is. And let's assume the Earth has a radius of 6.3 times 10 to the 6th meters, which is also exactly what it is. So what the spaceship captain needs to figure out what velocity does a 2-ton rocket need to be going as it leaves the surface of the Earth for it to get all the way out of Earth orbit. And some things to remember here. First of all, remember that you can use gravitational potential to figure out gravitational potential energy. Second of all, you can ignore air resistance. So there's no external forces. So remember that you can convert directly from kinetic energy to potential energy. So now that you've had these hints, pause the video and then see what you can do. Let's start by writing out all of our equations. We know that kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. And we know kinetic energy is 1/2 mv squared. We know that potential energy is mgh for a constant g, or potential energy is negative mass times the gravitational constant over radius times mass 2. And that's the equation for gravitational potential times mass. And in that case, we need to do a change in potential energy. And change in potential energy is just potential energy final minus potential energy initial. So this seems a little tricky. So let's go a step at a time. What's kinetic energy final? Well, it can be whatever we want, but we want as low a starting energy. And since our kinetic energy, once we're out of the system, doesn't matter, we'll just say kinetic energy final equals 0. So what's our kinetic energy initial? Well, it's 1/2 mv squared. And in this case, the mass is 2,000 kilograms. So we can say kinetic energy initial is 1,000 joules times whatever velocity squared is. So let's hang on to that and remember it, because that's going to be really important. So now, let's go back to our original equation. Potential energy initial plus kinetic energy initial equals kinetic energy final, which is 0, plus potential energy final. So let's see how can we manipulate that. Let's get kinetic energy on its own. Kinetic energy initial is potential energy final minus potential energy initial. Now what does this look like? This is just change in potential energy. So we can actually write this as 1,000 velocity squared, because that's our kinetic energy initial, equals change in potential energy. Now if you remember, what's the formula for change in potential energy? Well, just mass 1 g over r times mass 2, and then that's negative. So let's figure out what these values are. Final. Potential energy final is negative mass of the Earth, call that m sub e, so we don't have to write it out, times g over infinity. This is once we've gotten all the way to infinity, times 2,000 kilograms. Well, here's the thing. All of these are finite. None of them are infinite. So that's a finite number divided by an infinite number, so it just equals 0. That's pretty simple. Now, potential energy initial's a little trickier. We say negative mass of the Earth, which, as we said, is 5.9 times 10 to the 24th, times the gravitational constant, 6.7 times 10 to the negative 11th, divided by the radius of the Earth, which is 6.3 times 10 to the 6th meters. Now, what are we forgetting? Wait a second. We're forgetting the mass of the satellite. So all this times 2 tons. So let's multiply 6.27 times 10 to the 10th. So this is our value for our potential energy initial. And that actually should be negative, because we're forgetting the negative sign here. So 0 minus negative that value. That's our change in potential energy. The negatives cancel, so our potential energy has increased by 6.27 times 10 to the 10th. And this has to be equal to our kinetic energy initial, because that's what we calculated. So we go back, we say kinetic energy initial is 1,000 velocity squared, 6.27 times 10 to the 10th, divide through by 1,000, velocity squared, 6.27 times 10 to the 7th, and then we just take a square root, which gives us the answer that velocity is 7.918 meters per second. Now 7.918 meters per second, sorry, 7,918 meters per second is about 8 kilometers a second, which is about right for escape velocity. So if there was no atmosphere and you could get a rocket going 8 kilometers per second on the surface of the Earth, it would go up and never come down, and you would actually violate the truism that whatever goes up must come down. So you should be really pleased with yourself. You've now covered enough physics that you can plug everything you know together to get to this answer. So that's pretty cool. So you now know what you need to know in order to do exchanges with conservation of energy.